Welcome back. In this section, we'll be talking about some more applications of exponential functions, in particular, exponential growth and decay. We'll also be talking about logistic equations towards the end of this section. To begin with, exponential growth, or uninhibited population growth, is a kind of growth where there's nothing to slow the growth, and there's no upper limit to how big the population can grow. So if you're imagining what the graph of that kind of a population might look like, it would be something that has an exponential shape to it. As our time goes onwards, the population just increases without any upper bound to it. There's nothing to slow it down, so it just gets larger and larger and larger. The formula that we have for uninhibited growth or exponential growth says that A of t, the size of our population after time t, is made out of just our initial amount, a0, multiplied by e to the power of kt. T is time, and k is our growth constant. K controls how fast or how slow our population is growing. To be a growth constant, k needs to be positive. If k were negative, then our population would be decreasing over time. We would have a shrinking population. So we have a formula here for uninhibited growth, and it happens to look very similar to one that we've already seen. In the previous section, you've seen the formula for continuously compound interest. Amount of time t is our principal times e to the rt. And you'll notice it's pretty much the same formula. And that's because continuously compounded interest is an example of uninhibited growth. If you were to plot how much money you have in the bank after time t, that amount will just continue to increase forever. As long as you're leaving the money in the account and as long as it's continuing to gain interest, it will just get larger and larger and larger as time goes on. And you can see also that our growth constant k is just the interest rate. So our interest rate for continuously compounded interest, that controls how fast our bank balance is growing, just like how k, our growth constant, controls how fast the population is growing. So in this first example, we have two bits of information given to us. One is that we start out with 1,000 bacteria, and then 1 hour later, we've got 6,500 bacteria. And we're assuming that we've got uninhibited growth, exponential growth. So what we want is the formula for A of t, the number of bacteria in the dish after t hours. So time is being measured in hours. So we know two things. Again, number one, the initial amount that we had is 1,000. And since time is being measured in hours, then we know that after 1 hour, when time is 1, the population is 6,500. And I'm going to use both of these facts in order to solve for my unknowns in this formula that I have for exponential growth. The first unknown is my initial amount, and that we were just given, so that's the 1,000. But I still have a growth constant k that I need to find, and that's where I'm going to use my second fact, that 6,500 bacteria will be in the dish when time is 1. So we'll have 6,500 bacteria when t is equal to 1. So we'll have e to the power of k times 1, or just e to the power of k. And now to find my growth constant, I just need to solve my equation. So solving the same way that I did in the previous sections, I'll first divide both sides by 1,000 so that I can isolate the exponential function. And then I'll rewrite it as a logarithm. Since it's base e, then I'll be using a log with base e, which is natural log. Switching inputs and outputs. And there we go. I've got my growth constant k, which is natural log of 6.5. I'm not going to run that through my calculator because if I'm looking at doing any calculating with the exponential growth formula, I'm going to have a value for t that I'll need to put in, and at that point, that's when I'll calculate out what is natural log of 6.5. I don't need to bother calculating it right now. And also, if I calculated natural log of 6.5, you'll notice that it's a decimal number, and if you wanted to use decimals, that means you're going to wind up rounding things off. And if we start rounding things off at this stage, if I round off what is natural log of 6.5, then that means any answer I get from this will be further away from the true value than if I had left things in terms of natural log of 6.5. So I'm just going to leave things there as natural log of 6.5. There's no reason why I need this to be a decimal number because, again, I've got a calculator. If I did need to find out what this is, that's when I'll use my calculator to do that for me. Otherwise, I'm not going to waste my time. So there we go. We have A of t. My formula for the number of bacteria is 1000 e to the natural log of 6.5 times t. We're going to do another example with this growth formula, but before we do, one thing I want to make clear here, and that's the exponent. This is a mistake that sometimes people will make, and that's when we're looking at the power, remember it's the growth constant times t, and our growth constant was natural log of 6.5. A mistake that people will sometimes make is to think that the t is now somehow inside of the natural log, but that's not the same thing as what we have. What we have is our growth constant, natural log of 6.5 times t. So that is not the same thing as t being inside of our natural log. That's why I was a little bit careful here when I wrote it, and I wrote my e to the power of natural log of 6.5t, why I put brackets around my natural log of 6.5. Because if I had just written it as natural log of 6.5t with no brackets, that's ambiguous enough that you might think that these are both inside of the natural log. So it's two solutions to prevent you from thinking that. One might be to put brackets around the log, or you could write it as 1000 e to the t times natural log of 6.5. That's also a little bit of a clearer way to write it, and it makes it clear that t is not a number that's inside that natural log. Okay, so now we want to find out for part B, how many bacteria will we have after 5 hours have passed? And we know that A of t, that told us how many bacteria we would have after t hours. That was 1000 e to the natural log of 6.5 times t. And we just want to know how many bacteria do we have when t is 5. So we just want to put in 5 for t. And then we just need to run this through our calculators. One thing, just as far as the calculation side of this goes, we want to make sure, of course, that all of this is the power that's on our exponential function e to the power of. So when I'm entering this in my calculator, I'll enter it as 1000 multiplied by e to the power of, and then I'll use brackets. Natural log 6.5 times 5, close my brackets. When I do that, I'll come up with approximately 11,602,906.25. And so we can say that in 5 hours, there will be 11,602,906 bacteria. One thing that you might be wondering about is, well, what about bacteria that might have died during those 5 hours? And that's something that's not part of our exponential growth formula. This is why it's uninhibited exponential growth. We're not taking into account any limits on the population size, and we're also not taking into account any bacteria that might have died. So if you're thinking about what the assumptions are, we're just assuming that once something is created, it will be there forever. So these bacteria never die in our minds, at least. So that's why we've got 11,602,906 of them. Does this match reality? Maybe, maybe not. And so one thing that's also true about mathematics is that sometimes when we're looking at a model for something, in this case, this is a model for population size, the formula might be simple, but that's because we're avoiding some of the more complicated realities of it. And that if you wanted a formula that closely matched reality, it might not be as easy of a formula to work with. So there's always a little bit of a trade-off here. Exponential growth, our formula is an easy one to work with, but that's because we've traded off a few things here. Namely, we're not bothering to think about limits on population size or members of the population not surviving. We're not worrying about that at all. All right, so now we're interested in how long does it take for our population to double in size? We originally started out with 1,000 bacteria, and we want to know at what point do we have twice that amount? At what point do we have 2,000 bacteria? So we're looking to solve for t here. Also, and this is more towards the end of things, we want to give our answer in terms of minutes. We want to know how many minutes does it take for us to have our population double in size. We have to remember that here for our formula, when it was originally defined, we had it defined where t was the number of hours that we've had pass by. So when I solve for t in my exponential growth formula, I'll find the number of hours it takes for it to double in size, and I'll need to figure out what that is in terms of minutes afterwards. So to begin with, we know that we have our population at time t is 1,000 e to the natural log of 6.5 times t. And we know that we want our population to be 2,000. So we want to find out at what point is a of t equal to 2,000. And I'm going to just solve for t now, first by dividing both sides by 1,000 to help me isolate that exponential function. And then I'm going to rewrite this equation as a log. So instead of e to the power of, it will be log base e, or natural log. And I'll switch the outputs and the inputs. And I can solve for what t is here. It should be then natural log of 2 divided by natural log of 6.5. And that gives me about 0.37031. And this is in terms of hours. But the one thing I need to remember here is that if we're looking at 0.37031 hours, that for every 1 hour, there would be 60 minutes. And so that means that what we would have would be something in terms of minutes now. 0.37031 times 60 over 1 gives me about 22.218 minutes. So it takes 22.2 minutes for the population to double. All right. Let's start off with another one. This one is about Streptococcus bacteria, and this is actually roughly true. The doubling time changes depending on some other conditions, temperature, food, and all the rest. But in general, for Streptococcus bacteria, the doubling time is roughly 45 minutes. And so we've got a population of these bacteria, and we're going to assume that we've got exponential growth. And A of t represents the size of this bacteria colony after t hours. So we don't know what the initial amount is. That's a mystery to us. But one thing that we do know is that when we've had 45 minutes pass, or in other words, at 3/4 of an hour, we should have twice the initial population, because we know that our population will double in size. So whatever our initial population is, after 45 minutes, we'll have twice that. And the other part that we need to keep in mind, of course, is that my time is being written in hours. That's why I've written the time as 3/4 rather than 45 minutes. 45 minutes is 3/4 of an hour. So we know that our formula, A of t, is A0 e to the kt. And we know that we'll have twice the initial amount when time is 3/4. And so no matter what the initial amount is, I would be dividing both sides by it. So the fact that I don't know what the initial amount is, that's actually not a problem. Divide both sides by whatever the initial amount is, and I have 2 equals e to the 3/4 k. Or in other words, natural log of 2 equals 3/4 k, or k is equal to 4/3 natural log of 2. And there we go. We've got our growth constant. Our growth constant k is 4/3 natural log of 2. And so now what we want to do is use this growth constant to solve this problem. We start off with 500 bacteria. So that means that A of t should be 500 e to the 4/3 natural log of 2 times t. And the question is, how many hours will it take for our population to reach 1 million? So I want my population to be 1 million, and I need to solve for t. Okay, so I'll do the same thing that we did always. I'll first isolate my exponential function. I'll divide everybody by 500, which leaves me with 2,000. 1 million divided by 500 is 2,000, and then I've got e to the power of 4/3 natural log of 2 times t. And then I'll rewrite this as a log base e, or natural log, switching the inputs and the outputs. And then away I go. I can solve for what t is. It's natural log of 2,000 over 4/3 natural log of 2. Or if you like it looking better this way, you could say it's 3 natural log of 2,000 over 4 times natural log of 2. However you want to do it, that will give you your answer of about 8.22. So 3 times natural log of 2,000 divided by 4 times natural log of 2 gives us about 8.22, or in this case 8.2. We're rounding it to 1 decimal place. So it'll take 8.2 hours. So if we have some strep bacteria in a dish, if we start with 500 bacteria, then about 8 hours later we will now have 1 million of them.